In the last class, we discussed about the models of say shared memory, and then we also discussed on mesh connected computers and perfect shuffle computers. Today, the first model what we will be discussing is known as butterfly model. It consists of k plus 1 2 to the power k processors. Okay, the pros and this processor divided into k plus 1 rows, and each row contains 2 to the power k processors. Now the rows are numbered 0 to 0, 1 to k, and also the processor in any row are indexed as 0, 1, 2 to the power k minus 1. Okay. Now let us assume that Pij is the jth index processor in ith row. Now this processor Pij has the 4 connections. One connection is Pi minus 1j, another one is Pi plus 1j, provided it exists. Pi minus 1m and Pi plus 1m, provided it exists. Where m is obtained, where m and l are obtained as by inverting ith MSB of J obtained by inviting ith MSB of J and inviting I minus 1th MSB of J respectively. Okay. So Pij is connected with the at most 4 processor, Pi minus 1j, Pi plus 1j, Pi minus 1m and Pi plus 1l, where m and L are as follows. M is obtained by inviting ith MSB of J and L is obtained by inviting ith MSB, I minus 1th MSB of J respectively. Now by MSB, ith MSB means that actually if we start with that B1, B2, BQ or BK, these are the K bits you have, because it's a 2 to the power K processors you have. So K bits, this is the 0th MSB. Okay, this is the first MSB and so on. Now let us consider we have say K equals to 3, that is number of processors is 32 number of rows is 4 and number of processors in each row is 8. So let us assume that you have row 0, row 1, row 2, and then you have row 3. You have processor 0, 1, 2, 3, 4, 5, 6, 7. So PI is connected, so you have P0, this is your row 0 is index is 0, 1, 2, 3. This side is your I, this side is your J. Okay, so P0, 0 is connected with P1, 0. So this is connected with this, this is connected with this. Okay, so these links are established based on these two connections. Now think about row 1, say this one, P1, 1, P1, 0, P1, 0. P10 is that so by inverting this you will be getting 1, because first this is the 0th bit, this is the first bit, this is the second bit. So you will be ith MSB you are replacing, and P will be connected to P0, P02, P02. First one is ith, I minus 1. So this will be connected to P0, P02, P10, it should be connected to, okay. So this is one thing you have to keep. This will be first, second, MSB is K. MSB will be K. So in that case, P10 will be connected to P0, P0, and here the first bit will be converting 1000. So P04, P04. Okay. Then you have P11, and it will be P05, P05. Similarly, you have P06 and P07. Now, what happens? P14, is P0 0 0 0. So P14 will be connected to this. Similarly, this will be connected, this will be connected to this, and this will be connected to this. Okay, so this is based on this connection. Now Pi plus L will give you the reverse connection basically. While I consider this one, this will give you that. So this is a bidirectional things it will show. And then you have, suppose P2, P21, P20, P20, it becomes P1, P1 and 0 1 0, P12. P20 is P12. Similarly, you will be getting this one, this you will get this one. And last one you will get structure is like this. Okay, so these two are basically to indicate the bidirectional link. So the structure of this this butterfly network, if you observe that this looks like a butterfly thing, the height of this is a log n plus 1, and this side you have the 2 to the power or n processors, and here you observe that to transfer the data from one corner to another corner, you will not take more than order log n time. And another thing is that this type of network is easily upgradable. What you need, you can add another butterfly here and you can plug it into that. Okay, only thing condition is that it should be in the form of k plus 1 2 to the power k. So suppose you given k plus 2 to the power k plus 1 number of processors, and you first obtain k plus 1 2 to the power k one cluster, the another cluster is k plus 1 2 to the power k, right? And then at the top you put k plus. So you get basically here k plus 1 2 to the power k plus 1 k, right? So basically you need additional 2 to the power k plus 2 to the power k plus 1 nodes to be fixed for additional things. So the thing is that converting or given to two butterfly networks, and you want to make it the next great upgradability things, you have to do little homework or bookkeeping to do that. Okay. The type of problem which you can solve on butterfly network is that you where you need the question of pipelining is coming, then you find that this network is very useful. Next model we'll be discussing is Hypercube. Here you have 2 to the power k processors, and each processor has k, each processor is connected with log n each processor is connected with k other processors. Now Pi is the say P0, P1, P2 to the power k minus 1 are the indices of the processors, and Pi is connected to Pj if J can be obtained by inverting a bit of the binary representation of I. Okay, Pi is connected to Pj if J can be obtained by inverting any bit. There are k bits you have of the binary representation of I. Okay, let us assume that suppose you have n equals to 8, so you have P0, P1, P7. Okay, so P0 is connected with, so you have the 0, 1, 2, 3, 4, 5, 6, 7. That is the binary representation of this is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Now P0 is connected with, by inverting, is 0, 0, 1, 0, 1, 0, 1, 0, 0, 0, 0, 0, 0, 1, 1, 1, 0, 1, 0, 0, 0, 1, 1, 0, 0, 0, 1, 1, 0, 0, 1, 0, 0, 0, 1, 1, 1, 1, 1, 0, 1, 1, 1, 0, 0, 0, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 1, 1, 1, 1, 0, 0, 0, 1, 0, 1, 1, 0, 1, 0, 1, and 0, 1, 1. So P0 is connected with these three processors because there are k connections. So if I draw this, P0, P1, P2, P3, P4, P5, P6, P7. P0 is connected with P1, P2, P4. P1, P2, P4. P1 is connected with P1, P0, P3, P5, P3, P5. P2 is connected with P3, P3, P0, and P6. P3 is connected with P2, P1, and P7. P4 is connected with P5 and P6 and P0. P5 is connected with P4, P7 and P1. P6 is connected with P7, P4 and P2. P7 is connected with P6, P5 and P3. P7 and P3. So this is the structure of your hypercube with with 8 processors. Now what happens when we have 16 processors? case of 16 processors, you will be adding another zeros here. And here also there will be 0. There also will be another 0. And you will have another 1, 1 0 0 0, 1 1, 1 0 0, 1, 1 0 1 0, 1 0 1 1, 1 1 0 0, 1 1 0 1, 1 1 1 0, 1 1 1 1. This is for 8%. Similarly, you can have remaining 8%. So here what happens, that you have connected already 8, now it is P0 is connected with P8. So I am drawing another one is P8, P8, P1 is connected with P9, and P2 is connected with P10. P3 is connected with P11. P4 is connected with P12. P5 is connected with P13. P6 is connected with 14. P14 and P7 is connected with P15. Okay. Now think about the 8 onwards. Eight is connected with 0, that is done. 8 is connected with 9. 8 is connected with 9. And 8 is connected with 10. And 8 is connected with 14. Eight is connected with 12. 8 is connected with 12. 8 is connected with 12. Okay. Now think about next one. 9 is connected with 8. 9 is connected with 11. 9 is connected with 13, and 9 is connected with 1. Next one is 10. 10 is connected with 11. 10 is connected with 11. And then 10 is connected with 8. 10 is connected with 8. 10 is connected with 8 plus 4 plus 2, 14. And 10 is connected with 2. Done. Then 11 is connected with 10. 11 is connected with 10, and 11 is connected with 9, 11 is connected with 15, 11 is connected with 15, and 11 is connected with 3. Done. Then 12. 12 is connected with 13. 12 is connected with 13. 12 is connected with 13, and 12 is connected with 14. 12 is connected with 14. What is 12? Twelve is connected with 14. And 12 is connected with 8. Yes, then 12 is connected with 4. Okay. Then 13 is connected with 12. Yes. Then 13 is connected with 15. And then 13 is connected with 9. Yes. 13 is connected with 5. Next one is 14 is connected with 15. 14 is connected with 12. Yes. And then 14 is connected with 8 plus 2 is 10. Okay. And 14 is connected with 6. Okay. Then 15 is connected with 14, 15 is connected with 13, 15 is connected with 8 plus 3, 11, 15 is connected with 7. So this is the structure of hypercube when n equals to 16. If you observe that this is basically a round shape, and one good thing of this is that given two hypercubes of size 2 to the power k, I can merge easily then with additional links of size 2 to the power k plus 1. Now one beauty thing is that, say, so you had this is initially you had this hypercube. Initially you had this hypercube of size 8. This is another hypercube of size 8, and you observe that for every processor there is one additional link you have established, and we can merge and we get the hypercube of size 16. Now if I have another 16 processors, similarly I can add these two sub-hypercubes to get a hypercube of size 32, and you will observe that you are adding only one additional link between the two processors. Okay, and these two processors are those ones whose binary representation MSB of the first MSB of the binary representation of the two processors, they are defined. Okay. So here every processor is having log n connections. If you have the n processors, in the case of butterfly, every processor is having at most 4 connections. in the place of two-dimensional mesh connection, every processor is having 4 connections at most, and in the case of perfect shuffle, every processor has at most 3 connections. Now next one is tube connected cycle. It is the combination of butterfly and hypercube. You have k into 2 to the power k processors. These processors are divided into k groups. Each group has 2 to the power k processors. These processors are indexed 0, 1, 2 to the power k minus 1, and groups are numbered as 1 to k. Pij is a processor, is the jth processor in the ith group. The processors of different groups, processors of different groups having same index J forms a cycle. That is, Pij is connected to Pi plus 1 mod Kj. Okay, I have P1 1, P2 1, P3 1, P4 1, Pk1. So this forms a cycle. Now in these operations, you observe there is a problem when it reaches k plus, when it reaches k plus 1, when I is Pk minus 1j is connected to, I will write P k mod k j, so this becomes 0. Actually P0 is basically your Pk. So what I have to write here, not the modulo operations, we have to write it in a different way, is connected to Pi plus 1 j if I is less than k minus 1. If it is I is less than equals to k minus 1, and it is P1j if I is 1. I is k. If it is I is k, then Pkj is connected with P1j. Okay, so that is the structure we have to write instead of modulo operations, because I have made it the group 1 to k, so I have to write Pij is connected with Pi plus 1j if I is less than equals to k minus 1, and P1j if I equals to k. So this forms a cycle, and besides this cycles, Pij is connected with Pij is connected with Pim, where M is obtained by inverting ith MSB of J. M is obtained by inverting ith MSB of J. So let us see, when you have 24 processors, that is K equals to 3, you have 24 processors, and the number of groups is 3, and each group is having 8. Each group is having 8 processors. So initially let me write P10, P20, and you have P30. You have P11, P21, P31. You have here P12, P22, P32. You have here P13, P23, P33, P14, P24, P34, P15, P25, P35, P16, P26, P36, P17, P27, P37. So this is obtained based on the initial connections that Pij is connected with Pi plus 1j if I is less than or equals to k, otherwise P1j if I equals to k, and P10 is connected with P14 because is first MSB. P20 is connected with P20 is connected with you will be changing the second one, P22, and P30 is connected with P31. Okay. Similarly, P11 is connected with P15, P21 is connected with P23, and P31 is connected with this. Now P12 is connected with P16, P32 should be connected with this. Now P13 is connected with P17. Now P24 is P26, Similarly, it will become P25. P34 will be connected with P35. P36 will be connected with P37. Okay. So you observe that every 3 processors, if I consider it is a single node, then it becomes a hypercube. If I consider this whole thing as a single node, this is a single node, it becomes a hypercube, and every processor is having 3 connections. One is or 2 is to form the cycle, and 1 is connected with other cycle. Okay. So this is all about the cube connected cycle. Now the next model is known as linear array. Here if you have n processors, the P0, P1, Pn minus 1, they are linearly connected. It means Pi is connected with Pi minus 1 and Pi plus 1, provided they exist. The structure looks like you have P0, P1, P2, Pn minus 1, and these connections are bidirectional. The next model is tree model. Here you have 2 to the power k minus 1 processors. Now these 2 to the power k minus 1 processors are arranged in such a way that it forms a full binary tree, and this binary tree are indexed based on the breadth first searching number. That is, P0 is the root, P1, P2, P3, P4, P5, P6, P7, P8, P9, P10, P11, 12, 13, 14, and so on. That is, Pi is connected with P2 I plus 1 and P2 I plus 2. Pi is connected with P2 I plus 1 and P2 I plus 2, and also it is connected with Pi by 2, which is the parent of this, provided they exist. Now height of this tree is log n, that is height is k. It indicates that to transmit the data from bottom to up, you need order log n time. Now the next model is pyramid model. There are 2 types of pyramid. One is one-dimensional pyramid model. It is the combination of linear array and tree. You have the usual tree, and these siblings they form the linear array. And it gives you the one-dimensional pyramid. Now next model is known as two-dimensional pyramid. And it is the combination of mesh and tree. And every processor Pi has at most 9 links. You remember that you have P0 and it has 4 children. Now for this node you have again so every node you observe that this is a mesh, this is a mesh, this is another mesh and so on, and in this a node of this mesh is connected with the 4 neighboring processes on the mesh, it is connected with this parent and also it is connected with 4 children. So a mesh is having in 2-dimensional pyramid, it is a combination of tree and the pyramid and the mesh, and for each node it has at most 9 connections, 4 connections of the same level maintaining the mesh connectivity, 1 is to its parent and 4 is to its children. Now these are the major SIMD models. Now let us come to this definition of MIMD. Multiple instruction stream and multiple data stream. Here you have several independent machines. Each machine will have the control units C1, C2 and Cn, this n control units, and you have that processor P1 attached to control unit 1, processor Pn is attached to control unit n, and you have these processors are connected either through shared memory or interconnection networks or shared memory. Okay. Now each processors are capable enough to solve a problem. Now here only issue is that while the control unit 1 broadcasts one stream of instructions, control unit 2 can broadcast the different set of instructions to be performed, and as a result the synchronization plays a major role, so the delay becomes very less, and since this processor is capable enough to solve the problems, so each control unit broadcasts the set of instructions as much as you can, so that the communication between the two processors becomes minimum. Now once you have the model based on the interconnection networks, we tell it is a multi-computers. And the algorithm designed for this is known as distributed algorithms. And in this case, the message passing plays an important role, because once you pass the message, you should see that the other processors are active or it does not get disturbed. So minimum number of messages to be distributed or passed among themselves. So in order to measure the complexity, we measure based on the number of messages transmitted between the two processors. Now once we have another type of thing, that where the processor can communicate among themselves through shared memory, and in that case the model name is multi-processors, and the algorithm is known as asynchronous parallel algorithm. We have the asynchronous parallel algorithms, and here the time complexity is of the asynchronous parallel algorithm plays the role to measure its complexity. So these are the various types of various models you have in front of you for designing the parallel algorithms. Now, how to measure the complexity of algorithms? In the case of sequential algorithms, we measure the complexity of the algorithm based on the two factors. They are time complexity and the space complexity. And there exists a trade-off relationship between these two. If you have the more space time, possibly you can take less to solve a problem, or similarly, if you have less space, time can go up. So there exists a trade-off relationship between these two, but there is a limitation. Say, for example, to find the sum of n numbers, whatever the space you have, but you have to give the n minus 1 additions. Okay. Now, in the case of parallel algorithms, you have the another factor, the number of processors. Number of processors you are using. Now, here you have the trade-off relationship between the three factors, time, space and number of processors. It may so happen that if you have the more number of processors, time may be less, or if you have less number of processors, and you may find that time is taking up. But there is a limitation here again, that whatever the case may be, you have to pay additional cost for using more number of processors. Now, that in order to measure the gain with respect of the parallelism, there is a term known as speed up ratio. It is defined as the time complexity of the best known sequential algorithm it should be worst case time complexity of the best known sequential algorithm divided by time complexity of parallel algorithms. So more the value of speeder, better is your algorithm. Agreed? But the speed up, is there any limitation? Do you expect that there should be a limitation? That what we have defined, that worst case time complexity of the best known sequential algorithm divided by time complexity of the parallel algorithm, and I can I write this part be less than or equals to the number of processors used. Let us consider the problem of finding the summation of numbers on mesh connected computers, and as you know that I have a mesh of say n cross n, n cross n mesh, and suppose the number of elements I have n square. So n is n square, p is number of processor is also n square. So you observe that there are n square elements and n square processors. What I can do, I can distribute these n square elements among these n square processor, each is having one element, right. Now, in order to find the sum of these n square elements, first I will use or I will assume that this is a linear array and I will add them. This can be done ordered n time. So, you will observe that all the summation of respective row, they are available in the last columns. So, again I will add this, assuming that this is a linear array, I will combine them. So, this can be done in order n time. So, the total time becomes order n using n square processors to find the sum of n square elements. But if I estimate the cost of this method, it becomes, as you know, the cost is number of processors and the time required to find the sum of n numbers. So, which is nothing but n into order n. So, it becomes order n cube to find the sum of n square elements. So, it is not cost optimal because it is not cost optimal because to find the sum of n square elements using the sequential processor is order n square. So, can we obtain the cost optimal parallel algorithms? To do that, before doing that, let us assume that I have n to the power 2.5 n to the power 2.5 number of elements, 2.5 number of elements. So, what we assume or what we do, we distribute this n to the power n to the power 2.5 elements among this n square processors such that every processor contains square root of n elements. Now, if we observe that a processor is having a square root of n elements, so there are n square processors, so n square into n to the power half, which is n to the power 2.5 elements, you have distributed among the n square processors. Now, I employ each processor to find the sum of its n square elements, its square root n elements, right, which can be done in order n time. Sequentially I have done it. Now, every processor will retain the sum of square root n elements, which can be done in order square root n time. Now, these summed elements, now I can sum in row wise in order n time. So, you get again order n time to find the sum of square root n elements row wise, and in the last column you will find that sum of n square root elements in each row. Now, this sum can be added in order n times to get the using the array column array processors to get the sum of n to the power 2.5 elements. So, the complexity becomes order n time. So, cost becomes number of processors n square and time to solve this problem. So, n to the power 3. Now, you observe that if I have n to the power 2.5 number of elements to find the sum of this n to the power 2.5 elements using n square time, it takes order n time, and cost is better than that of sum of n square elements. So, can we do better than that? Can we get the cost optimal parallel algorithm using this idea? So, to do that, to do that, let us assume there are n cube elements. Now, these n cube elements are distributed among these n square processors. So, each processor contains n elements. So, the problem can be redefined as you have n square processors and n cube elements. These n cube elements are distributed in such a way that every processor contains an element assigned to him, which takes order n time, and then these sums to be added here one by one. While you are adding this, you can move this data, as if they are linearly connected. The next phase you add this, next phase you add this, and so on. So after order n time, you will be finding the sum is lying in this column, then you move this data here, then this, linearly you follow it, and you get another order n time. So in order to do that, you need order n time to find the sum of n cube elements, which is stored it here. Okay. So this is the time complexity to find the sum of n cube elements using n square processor, and the cost to find the sum of n cube is becoming order n square processor you have used, order n, so which is order n cube, which is the cost optimal with reference to the sequential algorithm, because it takes to find the sum of n cube elements, you need order n cube additions. Next model is Hypercube. That is a very simple idea, because we know that if you have Hypercube of size or dimension 2 of Hypercube of 2 to the power k processors, this can be thought as the combination of two sub-hypercube, each of size 2 to the power k minus 1, and for one pi, it is connected with pj, where that MSB of these two binary representations will be differing, right? So what I can think about that you can bring the content of pj into pi and add it. Similarly, for all PIs of this zone, I get the data from the other is counterpart and add it, and then what happens, the dimension is reduced from 2 to the power k to 2 to the power k minus 1, and now you have a hypercube of size 2 to the power k minus 1. This you divide into the two parts, each of size 2 to the power k minus 2, and again there exists the connection between pi with pj, whose second MSB is different, and again this data moves up and add it. So the size is reduced to a hypercube of 2 to the power k minus 2, and so on. After k iterations, you will find the data is available in the first processor P0. So here you need order. If n is equals to 2 to the power k, then you need order log n time to find the sum. Okay, but cost is becoming order n log n, because n processors log n time, so cost is order n log n. Now in order to find out the cost optimal algorithms, again here idea is same. You divide, suppose you have n elements, you define your hypercube of size n by log n. Each processor contains initially log n elements, and sequentially they find the sum of these log n elements, so which takes order log n time plus you need to find the sum, which takes order log n by log n time. Okay, so this takes order log n time, and this is order log n, and you have used the processor is n by log n. So cost is order n, which is cost optimal to find the sum of n elements using n by log n times on Hypercube. Today we will be finishing our lecture by considering considering the sum of n numbers on another model, which is known as perfect shuffle computers. You remember that in the case of perfect shuffle computers, it has three connections for each processor. It has three connections, and here we will be using the shuffle and exchange operations to perform this addition of n numbers. Suppose we have 2 to the power n is equals to 2 to the power k, n equals to 2 to the power k processors. Here for I equals to 1 to k, do for each processor. For each processor, alpha, do in parallel, d is equals to 2 to the power, or d is equals to alpha minus 1, AD is equals to a shuffle of I, BD is equals to a exchange of I, sorry, it should be D. AD is equals to a shuffle of D, BD is equals to a exchange of D, and AD is equals to AD plus BD. So basically, if you have AJ or J is equals to, or D is equals to 0, 1, 2, 3, 4, 5, 6, 7, and say the number is 3, 1, 2, 4, 7, 5, 6, 8, then A shuffle D, A exchange D, and then AD. So A shuffle D is nothing but shuffle of 0 is 0, so it moves here. Shuffle of 1, it moves to 2. Then shuffle of 2 moves to 4. Then shuffle of 3 moves to 6. Shuffle of 4 moves to 1. Shuffle of 5 moves to 3. Shuffle of 5 moves to 3, shuffle of 6 and shuffle of 8 is here. Shuffle of 7 is 8. Now exchange is here, you get 3, 7 and 7, 3, 1, 5, 5, 1, 2, 6, 6, 2, 4, 8, 8, 4. So if I add it, you get 10, 10, 6, 6, 8, 8, 12, 12. Next one is again, you do the shuffle of D. So it is becoming 10, it will come here, 10, it will come here, 6, and this will come here, no, 8 will move up, this 8 will be here, and this will be here, and this will be here. Now you perform the exchange operation and add, this becomes 18, this becomes 18, this becomes 18, this becomes 18, this becomes 18. This is an accident why all 18 has come. Anyway, then you get the shuffle of D again, and then exchange of D, you will find, and after that if you add, you will get 36. Okay, so this is the way you can do, because you observe that it takes order k times to find the sum of 2 to the power k elements, and this can be also obtained as a cost optimal parallel algorithm, because at this moment it is not cost optimal, it is order n log n algorithms. In order to get the cost optimal algorithms, you assume that you have n by log n number of processors and n elements. Initially you make it n by log n groups, each group is having log n element. Sequentially each processor obtains log n sum of log n elements, and then you proceed it. You can easily show that it takes order n time to find, it takes order n cost to find the sum of n numbers using the perfect shuffle computers. So you can try at your leisure time to find the sum of n using CREW model. CREW model. Here the condition is little different, that instead of finding the EI sum of EI for all I want to find out that EI has to be replaced by summation over AK. K is 1 to I, which is known as a cumulative sum. Basically I want to find out, you have A1, A2, A3 and so on. I want to replace A1 by A1. This is by A1 plus A2. This is by A1 plus A2 plus A3 and so on. So please try at home, if possible, to obtain the finding the sum of, given the n elements, you want to find out the sum of the finding the cumulative sum of these n numbers.